thank you again for joining the Earth Systems and Climate Change Hub in our science webinar series. In this month's webinar, we have Professor Stephen Swearer from the National Centre for Coast and Climate, and he's going to be presenting today on nature-based opportunities for climate adaptation in the coastal zone. And Dr. Stephen Swearer is Professor of Marine Biology and Director of the National Centre for Coast and Climate at the University of Melbourne. And the NCCC's research on climate mitigation and adaptation in the coastal zone is funded by and contributes to the Earth Systems and Climate Change Hub project, which is entitled Establishment of the National Centre for Coast and Climate. So without any further ado, I'll hand you over to Stephen to start the webinar. Thanks, Stephen.
You're welcome, and welcome everybody. This is my first webinar, so hopefully this will go over without too many hiccups, and I won't embarrass myself, through the ether. So I guess I'll just get stuck straight into it. So before I get going, I guess what I'm going to be talking about today, I just want to recognize that this is very much a collaborative research project that I'm going to be summarizing today, and it involves a couple of the postdoctoral research fellows who are funded through the center, through the NESP Hub, and that's Becky Morris and Teresa Kahnlechner. And this also involves collaboration with a coastal manager and engineer, Ralph Rube, and Marco Giselberti, who is he's actually basically an environmental engineer based here at the University of Melbourne. And I'm going to, just because I've scripted this first bit, so I make sure I get through the proper information, it's going to be really boring for you looking at me reading a script. So I'm going to mute my video for this first bit, but then I'll come back and be a little bit more interactive. So I'm still here, I'm just hiding myself. So what we're really trying to achieve here is ecologically engineering more resilient coastlines. And really what the problem is that many coastal areas globally, not just in Australia, experience a whole range of multiple environmental stressors. And these stressors reduce the capacity of coastal ecosystems to help us mitigate climate change in terms of carbon sequestration and in terms of adaptation in relation to responding to coastal hazards associated with climate change. Typically, we adopt a kind of a hard engineering solution approach, and these are expensive. They are a static or non-dynamic structure, and they are a short-term solution. Whoops, what have I done? Okay. Can you still hear me? Yep, okay. I think what I did is I muted you. Okay, say something again, Sonia. Oh no, I have. How do I unmute?
Okay, I was muted. Yeah.
Muted.
So you're
okay,
good.
Yeah,
sure you're all good.
Yeah. There's this problem of clicking on the screen that's on my slide versus the videos of everybody. Oh, yeah. And so what we need is we actually need a lot more information. So there's a fair amount of research needs, and those research needs are around trying to develop methods where we can harness nature to provide solutions for coastal protection, and ultimately then methods where we can restore these coastal ecosystems to help us in terms of carbon sequestration, or in terms of what are called blue carbon ecosystems. And ultimately, this research then is, in terms of an outcome and an impact, is to provide case study demonstrations about what can be achieved and where those outcomes can be achieved. And ultimately then is that can help inform national guidelines for design and implementation of ecological engineering solutions. And this is important because, currently we don't actually have national standards that allow us to adopt these non-traditional approaches for coastal protection and coastal defense. So humans and associated infrastructure in the coastal zone are threatened by a range of hazards, particularly erosion and flooding. And future climate change is predicted to increase the risk of these coastal hazards through rising sea levels and more frequent storm events. Simultaneously, coastal urbanization is increasing. Therefore, the impact of these hazards is greater as the amount and value of coastal infrastructure continues to grow. So with this combination of coastal urbanization and climate change, mitigating against current and future hazards is a big challenge facing not just managers, but also coastal communities. Armoring with hard engineering structures, as you see in these photos here, for example, with seawalls or breakwaters, are typically the current solutions for coastal defense. But the cost of maintaining these structures under future climate change scenarios are really significant. And to put this into a Victorian context, the Victorian coastal environment has on the order of over 1,000 seawalls, revetments, and groins along its coast. And it's currently estimated that maintaining these structures will cost over $630 million. So equally, the negative impacts of these structures on coastal processes and marine ecosystems is becoming increasingly realized. Okay, so we've got a hard engineering solution that come with potentially some costs. So in parallel, this has prompted research investigating the value of natural ecosystems. So that's what's indicated here in this figure here on the right, then in terms of mitigating process and response, such as biogenic reefs, sand dunes and beaches, and vegetation to provide protection against erosion and waves, with the benefit that these systems can adapt to changes in climate. And importantly, they can self-repair after major storm events, so they're dynamic. So for example, coastal vegetated habitats such as seagrasses, salt marshes, and mangroves, which are commonly referred to as blue carbon ecosystems, can reduce water flow and wave height as waves pass through the dense vegetation. And similar effects are caused by the rough surfaces of reef habitats such as coral reefs, rocky reefs, shellfish reefs, for example. So coastal vegetation in these reef habitats can also stabilize shorelines through promoting sediment deposition and or reducing erosion and movement of sediments. Furthermore, sediments can accumulate in association with coastal vegetation, and that can increase the height of the land relative to sea level, right? So we can get these accretions that reduce then the likelihood of flooding during storm events. Now, so this all sounds great, but the problem is that globally, these habitats are declining, okay? So we've replaced a lot of these natural ecosystems with built infrastructure, and this has prompted advocacy for restoring or creating habitats through what are called soft ecological engineering techniques as a tool for natural shoreline stabilization. And this then, the hope then is that that's going to provide additional ecosystem benefits. Typically, that's often the provision of habitat to support biodiversity. So some people have described this concept of ecological engineering as almost being on this, basically being on this continuum that ranges from hard to soft. Okay, so in principle, hard ecoengineering is a solution to the ecological impacts of built infrastructure in areas where there really isn't an option to manage shorelines using soft engineering techniques. So this is an example here on the left here, where coastal cities that are densely populated, this happens to be from Sydney, where there may not be enough space available to create or restore habitats for coastal defense. Equally though, these eco-engineered habitats can be retrofitted, as you can see in this photo. This is some work that Becky Morris did when she was at the University of Sydney, where they were involved in retrofitting these seawalls, in this case with these flower pots, to provide tide pools to support intertidal associated organisms. So hard engineering has different objectives to soft engineering, in that ecological principles are integrated into the design of existing or planned defense structures, such that the motivation is enhancing biodiversity and ecological functioning to create multi-purpose infrastructure. Okay, so not just in this case a retaining seawall. So provide these other benefits in addition to maintaining defensive services. Conversely, while soft eco-engineering is generally advocated as the preferred approach from an ecological perspective, foremost to the creation of these sorts of habitats is the need to provide sufficient coastal protection in the future if this technique is to replace or complement artificial defenses. All right, so the key there is that we typically think about these sorts of natural habitats for other purposes, and it's around the extent to which we can understand the degree to which these habitats can also be used for defensive purposes. And We can also potentially get a hybrid approach. There may be areas where an entirely soft approach may not be possible, but we might be able to integrate, in this case, a shellfish reef in a seawall context that might actually improve the longevity of that structure. So despite the significant limitations of hard coastal defense in a changing climate, these structures are continuing to be built with little changes in practices or management. And one barrier to the wider use of a soft eco-engineering approach for coastal defense is evidence that restored or created habitats function in an equivalent way to, firstly, the intact natural habitat, and secondly, to hard engineered structures. And in response to this, the work that we did here, and this is, if you're interested in reading more about this, the citations at the bottom of this slide, we set out to synthesize basically all the work that's been published on the effectiveness of coastal defense using soft engineering versus hard engineering approaches. And the focus was on 6 different habitats, as you can see in these slides: sand dunes and beaches, salt marsh, mangroves, seagrass and kelp beds, coral and shellfish reefs, which have been identified as potentially important in mitigating coastal hazards. Now, it's important to note here that while these may be termed soft engineering methods, some of these habitats are hard substrate species. So for example, like corals and seaweeds and shellfish. And so restoring these sorts of habitats is predicated on the availability of that kind of hard substrate in order to facilitate the creation of these habitats in areas where they don't exist or where they've been lost. Okay, so what this figure here is showing is this literature search. And firstly, what we did was we wanted to find papers where on the restoration or creation of these habitats, okay, to determine the proportion of projects that restored or created. So they weren't just assessing these ecosystem service benefits from these habitats more broadly in areas where they naturally occur. We were very much focused on trying to understand what's actually been done in terms of assessing whether these ecosystem services are being provisioned when these habitats are either being restored because they've been degraded or where they've been created newly in areas where they didn't occur previously. So this is a heat map of the results of this analysis. So basically the hotter colors, as you can see on this scale on the right here, is the number of studies that report restoration of the particular habitat, which each of these are a row then for each of the habitats listed on the left, being the primary management objective of that study. Okay, so when we move down to coastal defense over here on the right part of this slide, what you see is that dunes, in particular here, are actually predominantly restored for coastal defense. Salt marsh and oyster reefs, which are in this kind of more purpley color, also aren't doing too badly in comparison to other ecosystem services. But there were few studies for coral reefs and mangroves and none for macroalgae and seagrass. Okay, so what you can see here is that most of these lighter colors are actually really around testing methods for restoration, simply restoring the habitat as being that primary driver and not actually related to coastal defense. So when we look at those studies that had stated coastal defense as the primary management objective and saw how many had actually had field measurements of whether or not that restored habitat had been efficient at coastal defense, what you see is that there actually isn't that much that's actually been done. So what you can see is that the number of studies go down. So there's actually only, mostly in relation to sand dunes, but what you can see is the shading in all those studies declines. So even though they may have said the purpose was for coastal defense, they didn't actually quantify a coastal defensive benefit directly. And if you then look at studies that actually compared the performance of those natural habitats against an artificial alternative, almost no studies have actually done that. So if we look at this in a different way, about 50 to 60% of the coral reef and mangrove and salt marsh studies measured coastal defense. And for shellfish and dunes, this was higher at around 80 to 90% of the studies. But only one study, this one right here by Gitman et al., actually made a comparison to artificial structures. So this study made a comparison between the damage to bulkheads and restored salt marsh after a hurricane. And what they showed was that the salt marsh suffered much less damage and was able to self-repair, right? So able to adapt. And this happened within a year. So the study really exemplifies how soft engineering structures should be evaluated for coastal defense. And ideally, what we would like would be to be able to make comparisons between artificial and soft engineered structures under the same environmental conditions. But, however, one of the challenges here is that the comparisons, because there weren't any studies that did this, so they basically weren't doing this, we had to make comparisons between effect sizes. So the measured response of different studies that looked at the effectiveness of soft or artificial structures at mitigating a hazard. So basically what I'm saying here is that because there aren't studies that directly compared soft to an artificial or hard engineering solution in the same study, the only way we can do is look at how effective these structures might be, independently of each other by pooling studies that have looked at one or the other. And we focused then specifically on studies that actually measured two responses, the first being attenuation of wave energy and the second being sediment stabilization. So the bottom probably doesn't really matter to most of you. Again, you can look at the paper in more detail, but effectively what we're talking about here is comparing studies where they had, for example, a shellfish reef, and they're looking at, in comparison to a control or reference location. So this could have been a before, so an area before they restored an oyster reef, or they had a control site where an oyster reef had not been established. And they then measured at these two locations how the shoreline responded. So in a perfect world, or if things went according to plan, we would see less erosion and potentially more sediment accretion in an area where an oyster reef had been restored in comparison to a nearby control location. Now, some of these studies went over several years, so they had long-term records of how that shoreline response might change through time, but the studies actually didn't focus specifically on the effects of those. Oh, and actually what that allowed them to do is have capturing some more extreme weather events, but unfortunately none of the studies focused specifically on shoreline responses to those extreme events. The second factor that we looked at then was wave attenuation. These are just the search terms for how those studies were revealed. But effectively, what happens is you have a propagating wave train that's coming on shore, and the idea here then is that some of these structures actually absorb some of that wave energy, and that's what's called wave attenuation. So the question then becomes: is there a reduction in that wave energy as that wave passes across that habitat as it moves shoreward? So this is a map then of where these studies have actually been done, and it's a fairly striking pattern, and it's not atypical of a lot of other research disciplines, that a lot of the work's actually been coming out of the United States in this case, and almost 75% of those studies from the US were actually on soft engineering versus artificial structures. In Australia, there are only really a few studies. Most of them have been on dune restoration, and a couple on artificial, assessing effects of artificial habitats or artificial structures, and none of them on any of the other natural habitats. And overall, the numbers of studies are pretty low that have actually done this, and the majority of them have been done in the United States. So what we have here is two different ways in which we could assess the performance of these studies. The left-hand side is a formal meta-analysis where we actually had data that we could extract from these papers to compare the response, in this case, for example, salt marsh in a restored versus a reference site, oyster reef, sand dune, coral reef, and breakwater. And what you can see in this plot is that there are data points that show, this is what's called a log response ratio. You don't really need to worry too much about what that is if you don't know what it is, but effectively the positive values indicate that there was a positive shoreline response, in this case a decline or in erosion, or actually positive accretion relative to a control site. If the error bars cross the dotted line over 0, then that indicates that that result was not significantly different from 0. Okay, so in this plot, what you see is that both breakwaters and coral reefs resulted in a positive shoreline response, whereas the other studies that were available showed no significant response. If we look at the qualitative analysis, so this is the proportion of studies that cited evidence of accretion, with significant differences according to that structure. So again, that's what's indicated here and along the left-hand side of that plot. So all studies on mangroves reported accretion following mangrove planting, which in some cases were in combination with a temporary breakwater to facilitate mangrove establishment. And a great proportion of studies on emergent breakwaters, which is kind of interesting. So that's the E breakwaters versus S breakwater, which is submerged, found a proportion of studies that were significantly elevated for accretion, whereas the submerged ones actually performed poorly and actually were erosive. So the opposite of what was the intended purpose of that hard structure. And seawalls also showed a greater likelihood of showing negative effects of installation of that structure. So that's in terms of shoreline. Whoops. Now, how do I get back? There we go. In terms of wave attenuation, breakwater, in terms of the formal meta-analysis, the breakwater significantly reduced wave height by 45%. And however, there was no significant detectable effect of studies on salt marshes or oyster reefs in terms of reducing wave energy. Importantly, though, the magnitude of that effect, even though not significant, was on a comparable level to a hard engineered structure, in this case, a breakwater. For salt marsh, both of these results is in direct contrast. So both the results of the percentage of studies and also the magnitude of that effect is not consistent with other published studies that have looked specifically at salt marshes as natural habitats, not so much in terms of restored ones. And so what this highlights is that we really need a lot more studies that are specifically focused on restored or created habitats to get a more concrete, if you like, or more compelling data that we can actually test these assumptions about the value of soft engineering solutions. So sort of to summarize this, what we find is that currently the evidence for the efficacy of restored natural habitats versus traditional infrastructure suggests that, at least in some instances, such as restoring coral reefs, mangroves, and sand dunes, could be equivalent to artificial structures at maintaining or building shorelines. The effect of salt marsh and oyster reefs was, however, more variable and did not show a significant effect on shoreline response or wave attenuation in comparison to breakwaters. So we found that a greater proportion of studies on seawalls and submerged breakwaters reported erosion actually compared to accretion. And these are structures that are commonly and increasingly used for coastal defense, but equally can result in these cases adverse impacts, at least in some areas. Notably, though, it's difficult to make comparisons between the structures that have not been tested under the same environmental conditions. So this is this last point here. So it does make it hard when, in many of these studies, for example, the soft engineering structures were tested under pretty benign environmental conditions. So under microtidal and low energy conditions, where in comparison, many of the artificial structures are specifically put into areas that often have much higher tidal and wave energy conditions. So it does make these direct comparisons difficult particularly across studies. What this suggests is we really need more rigorous data that assess the costs and effectiveness of habitats created for protection to mitigate coastal hazards. Uptake of any sort of nature-based coastal defense approach is going to require it to become an accepted alternative to traditional engineering solutions. And for this, we need more experimental trials that can be facilitated through collaboration among stakeholders, such as research institutions, coastal managers, and coastal engineers. So I'm going to segue now into this kind of broad overview to use this kind of as a justification, if you like, to present some kind of not completed, but currently underway case studies that we are currently implementing through the ECCC in Port Phillip and Western Port Bay, specifically to try to help move this, in our minds, this research agenda moving forward. One of these case studies is, well, one of the case studies involves some trying to restore white mangrove in 3 locations in Port Phillip and Western Port Bay. And the other case study, or second case study, is about trying to restore or create a submerged shellfish reef to protect an eroding cliff line. Case study 1 is around trying to, as I said, address a current challenge of an eroding shoreline that is placing both natural and built assets at risk. This figure right here on the left is for those of you not familiar with Port Phillip Bay, this is Altona. This is in the northern part of Port Phillip near Williamstown. This is very close to the city of Melbourne, where these colored lines represent where, from aerial photography, where the shoreline was from 1949 to at present, which indicates that this shoreline is eroding at about 1.5 meters per year. And the local council is concerned about protecting this coastal wetland and coastal park and wants to come up with some sort of coastal armament. Mangroves have traditionally been found in this area, particularly in Coral Creek, which is this waterway to the northern part of this eroding area. There was a major oil spill back in the 80s that resulted in the death of a lot of that mangrove, and it has been very slow to recover and regenerate. We are trialing and working with a series of structural engineers and design engineers to come up with a range of different built structures, if you like, or mangrove pods to help increase the likelihood that we can get mangrove recruitment and survival in these areas where we're losing sediment and we have wave energy conditions that are probably too strong to get them initially established. The purpose of this study then is to measure a whole range of ecosystem services, which I've listed here on the right-hand side of this slide. And what we will then do is quantify wave attenuation, sediment accumulation, shoreline change, or at least where the shoreline currently is, and ultimately then the survival of mangroves, the productivity of those habitats, the associated biodiversity, and the amount of carbon associated with those sediments in these locations before and after we establish mangroves in one location relative to the other. So ideally, opportunities will arise where nature-based defense could be compared directly in the field to an artificial structure. And so this is what we're truly trying to do, is actually, since we're going to be establishing these areas, we'll have adjacent areas where we can at least compare to shorelines that are experiencing this environmental change in the absence of any protective natural structure. But ideally, these would be done in areas where we can compare their performance relative to engineered structures. And this could then be done to provide a much more rigorous cost-benefit analysis of the effectiveness and the costs associated with these alternative approaches. While although soft engineering structures offer the potential for low impact, effective coastal defense, until there's a greater number of studies globally to test the value of these shoreline protection schemes, their wider use in place of artificial structures is likely to remain relatively limited. Another big issue that we've had, particularly in Victoria, and be interesting to see if others on the line might have experienced this as well, is around how much social license we actually have to adopt alternative approaches for shoreline protection. Mangroves are a contentious habitat in some areas of Victoria, and trying to get community support for increasing mangrove cover in coastal areas can be a challenge. And so another component of this project is actually spending a fair amount of time in community engagement and consultation around what we're trying to achieve to try to get stronger community buy-in. We've also been, just as an aside, we're also working with New South Wales Department of Primary Industries on some work that they're doing up in Ballina, where they've been using a combination of snags and rock fillets to try to increase and facilitate mangrove restoration in tidal creeks. And so part of this then again is going up to be able to measure a whole range of ecosystem service benefits before and after these works are actually going in place, so that we can actually measure and add that data back into this broader cost benefit analysis. The second case study involves this submerged breakwater shellfish reef or mussel reef that has recently gone in on Port Arlington, which is down in the southern part of Port Phillip Bay. This is work that's being led, as I mentioned, by one of the collaborators. This is Ralph Rube, who's pictured here in the lower left. He's actually undertaking, as a mature age student, a part-time PhD at the University of Melbourne. But he's the senior environmental engineer for the City of Greater Geelong Council. And Ralph's led a number of attempts to protect this particular foreshore, which has started off with a whole range of common approaches used by many coastal councils, including sand fencing, beach renourishment, building berms with coir logs, which you can see in this photo right here. When he then proposed, when a lot of these have actually failed, to try some alternative approaches. And this is what's pictured here, which I'm going to give you a little bit more information about. This offshore submerged breakwater or reef has turned out to be in modular construction, and we've used a mix of rock and recycled shell material within steel cages, which we're basically using this as an experimental opportunity or case study to try to increase the conversion of this hard engineered structure into a submerged shellfish reef. Okay, at this point I will try to figure out how do I unmute bring my picture back. Here we go, show myself. All right, I'm back. Okay, so just to put this into context, so I'm currently sitting up here in Melbourne. Port Arlington is here on the top end of the Bellarine Peninsula, just east of Geelong. Along Ramblers Road, so there's a row of homes here, and what you can see from these lines are the changing shoreline profile along this cliff face. Back in 2005, the cliff line was quite far seaward of where it currently lands. And what's actually happened is, if you're probably not familiar with this area, but there is a sediment compartment where there's a net eastward movement of sand. So you can kind of see the sand used to be here. It's now progressively been moving in a northeastward direction. And as a consequence, we now have an erosive cliff face that's approaching a whole series of homes. And obviously those people are concerned about the fate and future of their homes. So there's a built infrastructure risk. This sand movement and erosive cliff face has also been associated with a submerged habitat impact. In this case, there's been significant loss of sand stabilizing seagrass. This is a photo from 2005 showing a very extensive Zostra seagrass bed that has basically virtually been lost about 10 years later. This is a low-lying area that's subjected to winter storm inundation. And here are a series of photos of the water line about 2 meters from one of those homes along Ramblers Road, as well as coastal flooding. And here we're seeing a fair amount of sand loss and erosion during one of these storm events. So what the greater city of Geelong has been interested in is about, well, can we create more of an integrated living shoreline response? Can we incorporate a more holistic approach to how we manage coastal dune vegetation, as well as wetland and marsh habitat, primarily to stabilize and reduce sediment loss or aeolian sediment loss, and also any undercutting of these cliff faces during storm events. And also to have greater consideration of the impacts to coastal marine communities, because they have a beach, part of the problem is that they've got a beach renourishment program, and that sand, basically they have an ongoing sand supply to maintain a beach. That sand is mobilized and is having an impact on subtidal reef and seagrass habitats. So can they do better at working with the existing environment in relation to the terrain of the foreshore, the nature of the bathymetry in the nearshore environment, and a greater awareness and understanding of the morphodynamics and coastal processes that relate to sand transport and movement. So part of that then is around, as I said, it's around foreshore works that we're not involved in. That's about reshaping and revegetating low-lying areas. In terms of this semi-submersible breakwater, they've gone through the basic idea here then is to create a fairly long, several hundred meter long offshore breakwater that is just adjacent to this erosive cliff face. They explored a whole range of conceptual designs of how that offshore breakwater would be constructed. And this is an example here of a range of individual modules where there's potential for water movement between individual modules, but results in a predicted reduction in wave energy, some recirculation, and then as a consequence, potentially less undercutting and sand loss. They worked with Cardno, did a fair amount of coastal modeling to look at the predicted loss in wave energy as a function of this breakwater, as indicated here in these cooler blue colors. There was then a lot of discussion about the materials that this submerged breakwater would actually be made of. Here's an example of actually a largely failed geotextile reef that was put offshore of Geelong in Corio Bay. But there are a range of other sort of concrete-based designs that have been used in other areas. And here's an example of one that's a sort of caging version that's somewhat similar to what the council decided to use. And ultimately, the decision was around the extent to which the materials might influence the likelihood that these reefs are going to become a biogenic reef, the extent to which they can be found by other reef-forming animals, in this case, blue mussels or a tube worm, or calcifying tube worm, Galliolaria. So the city actually had access to a very large shell midden. So this is a whole series of oysters, mostly oyster shell material, but they also had scallop shell material, and they also had access to other recycled rocks, in this case, granite. They then created a modular reef cage design. So there's out in the paddock, a whole series of these cages that were constructed and filled with either mixtures of recycled shell and rock or rock only. This was the first layer of the reef cages as they were installed. And this is finally at the very end here, a video of them installing this first layer that happened about a month ago. What you can see here is that, so this is mostly scallop shell grit material, and what we've been able to do is actually design this in a way where it provides an opportunity to actually do some research. And so the construction of this breakwater then is a mix where we've added shell material into one half of this breakwater and not into the other half, and we're pre-fouling using tiles and mussels onto this shell material reef to see if we can accelerate the extent to which we can convert a grade engineered solution into a green one through this project. It's monitoring a whole range of baseline conditions and ongoing conditions as a response of putting in this breakwater. Some of the main concerns are around impacts to the sediment community and how that affects microbial processes, particularly in sediment, nitrogen and denitrification efficiency in the sediment, the extent to which the breakwater might facilitate recovery of seagrass and lead to a reef community that's more analogous to a natural reef habitat. There are a whole range of physical parameters that have been measured in terms of how the system is responding to the presence of this breakwater, with the key objectives then really being about building coastal resilience and providing a range of ecosystem service co-benefits. I will leave it at that. I would like to thank you for your attention. I would also like to thank the many other partners that we've worked with in terms of local councils and local government agencies that have made this project possible. And I thank you for listening. And I'm happy to take any questions. And over to you, Sonia.
Great, thanks, Stephen. That was really great. I just have one question in the chat box at the moment. Oh, I think another one's come in. So please feel free to write down your questions as we go, but I'll start with the first one from Ben. And Ben asks, are there any monitoring programs that exist currently that may be used to identify sites at risk of future coastal inundation? He says a lot of the work currently being done appears to be reactive rather than proactive.
Yes, I'm aware of, there's a range of studies that you can do that are much more proactive. So I can give you a local example within a Victorian context. They've actually created digital elevation models for the entire coastline for the entire state that were basically put onto the back of a really big LiDAR habitat mapping project that was then mirrored or meshed with some work coming out of CSIRO actually and members of the Hub where they created a coastal hazards model based on projections of storm surge and significant wave height from sea elevational changes to identify effectively where the hazards and the risks are likely greatest. It's still very much as many of you would know, this kind of bathtub approach. You're using a largely static coastline and making projections and predictions about where, at least under current coastal profiles, an intervention might be necessary. The Victorian government's approach to this data set has been largely then around also mapping the natural and built assets on top of that hazard map to make some informed decisions then about where limited resources should be put forward in terms of trying to mitigate those risks, because the risks outweigh greatly the amount of funding available. In the context of then trying to assess the likelihood of which interventions might be successful or not, that's something I'm less aware of in terms of the extent to which those solutions have been evaluated ahead of time in terms of the likelihood that you can actually achieve a desirable outcome. I don't know, did that answer your question? Is he still here?
I think so. He can write another question if that hasn't totally answered it. But we'll move on to the next one. So the question was around, can you comment on the life expectancy of the soft solutions? It was mentioned that hard solutions will eventually fail, but I imagine many soft solutions once existed. Oh, hang on, just lost it, sorry. But so mentioned that hard solutions will eventually fail, but many soft solutions once existed but have declined due to climate change. So it could be expected that new soft solutions might fail in the future under further climate change, but for example, the hybrid mangroves might be an example of countering this. Those are all very good questions. On the one hand, I guess it's important to recognize that a lot of soft engineering or ecological solutions are often dynamic in the sense that they are, they can be impacted and so they can be damaged, but that they can self-repair. So the question then becomes, under an extreme event, how much kind of buffering or amelioration of the hazard is achieved, how much of the habitat is damaged or lost, and what would the recovery time be projected based on natural recolonization and regeneration. There are examples, where there has been loss of habitats, whether, so mangroves that have been wiped out in a storm, for example, or a salt marsh, and the recovery times have only been on the nature of a year, several years. So it's, in the grand scheme of things, a relatively short natural recovery time. As your final comment there
the issues around climate change are a real one, in the sense that if you are using a natural habitat, that habitat has its own environmental envelope, if you like, a range of environmental conditions on which it can grow, survive, and thrive. And so therefore there will be potentially projections around changes in the distribution and biomass and availability or suitability of a particular species under a climate change scenario. I guess in a temperate environment, from like a mangrove perspective, climate change is actually great for mangroves down in Victoria. We're at the kind of marginal limit for white mangroves. So most of the climate projections suggest that conditions are just going to get better for mangroves, at least in Victoria. From the context of a hybrid solution, that's definitely one in which it potentially kind of buffers, if you like, the variation of how a natural habitat might respond to a hazard. And so to some extent, that kind of added buffering might mean that you see greater stability and persistence of that kind of integrated system over time. We just haven't had hybrid solutions for very long, so trying to make a valuation judgment of what the longevity of a hybrid approach might be is still very much up for debate.
Great. The next question is regarding the case studies that you talked about. Were approvals required to install the offshore options? And did these delay the process or cause any issues?
Yeah, yes, approvals, yes, you needed, yes, it's under the Coastal Management Act in Victoria. Yes, we needed coastal management consent. We needed approvals from DELWIP and from Parks Victoria. It is a long process. It did delay the initial. Well, it was a combination. So things took a little bit longer than we thought. And then what that did is it kind of pushed us into a condition where weather basically became more of an issue. So it wasn't too bad. The hybrid mangrove solution is one we're currently in the getting a management approval. So while one arm of the Victorian government has given us permission to go ahead and do this, and we have local councils that are keen, we still have to go through coastal management consent. We've gotten lots of intel, if you like, from other people who've had to do this about how to make the process as efficient and smooth as possible. But yes, it is a process. It can be, I guess, I don't know what's too bad. I mean, so it might take 6 months. In the case of the mangrove pods, I'm hoping a couple months. I'm cautiously optimistic it won't be too long.
And the next question comes from Robert and is runoff from industry or farms a problem for the many forms of soft infrastructure? Yes, it can be, right? So if it's a plant, depends what's coming down the catchment. In some situations, actually, for example, mangroves and salt marsh might be nutrient limited. So some runoff from farms, if it's a nutrient subsidy, can actually facilitate and make it easier for these habitats to increase in biomass and to spread. In other contexts, there at the sediment load, in relation to mangroves, that sediment load is important, and they can actually trap that sediment and actually they need that sediment budget, if you like, to actually accrete. And actually raise the shoreline. If there's no sediment input, you're not going to get accretion. But things like seagrass, for example, we've had big problems with this in Western Port, where the sediment load, because of changes to the catchment, have meant that we have a legacy of very fine sediments in Western Port that lead, because of the prevailing wind direction, we get a fair amount of wave fetch that resuspends that sediment. And so we've had a fair amount of seagrass loss, primarily because of light limitation due to high turbid water conditions because of sediment resuspension. So in some ways, what happens to the catchment can be beneficial, and in other ways it can be negative. And I alluded to the fact that we had an oil spill, so you can get contaminants. Use of herbicides through agricultural land can be really bad, and they can be still bioactive when they hit a catchment, and you can get a lot of loss of habitats
through basically being poisoned. So yeah, they are definite issues, and it is a risk.
The next question actually is from me. You mentioned that you did a lot of community consultation around extending out mangroves as sort of an option, and that there was some resistance to that by the community. Why was that?
Oh, they block my view and harbor mosquitoes.
Right.
Yep.
Okay.
Those are primarily the main ones. Yeah. So it's dealing with some of it's disinformation, and it's about how do you some people can be are willing to have a conversation and are willing to have their opinions changed. In other instances, it's an uphill battle. I mean, they've had in a Victorian context from trying to restore mangroves in Western Port. There's been what's called the Western Port Seagrass Partnership. They started with seagrass. They realized how hard that was, so they moved to mangroves. And they've had this one area around. It's an area called Lang Lang. It's a coastal area in the northeastern corner of Western Port Bay where this wave energy is really problematic. And they've been trying to get mangroves to establish in this area, and they've been working there for about 15 years to try to come up with a mangrove restoration approach that's going to work. But they've had years where they have community volunteers going out and planting thousands and thousands of mangrove seedlings, only to have some horrible, some irate local go in and yank up all their little mangroves. I mean, so you're just thinking, this is horrible. So there are some people who feel very strongly, rightly or wrongly so.
Okay, great, thanks. And the next question is, what was the background to where the city of Geelong sourced the large amount of shell midden material from? There was a picture of that, I think. Yeah,
it was just legacy, basically. It was in Geelong, so or actually it was near Queenscliff, I think, and it was just because there used to be, this a very productive scallop fishery, and they just all the fishermen must have come into. I think they came into Port Arlington historically, and everything got processed, on ship or right there on shore. And they dump all the shell there. So it was leftover shell material from a commercial fishery. So that just happened to be there, and no one was using it. And Ralph found out about it and said, "Can I have it?" And they said, "Sure." So, and actually, the other thing that it's been used. So the Nature Conservancy have been heavily involved in trying to restore native flat oyster reefs in Port Phillip. There are a range of oyster shellfish reef restoration projects throughout Australia. There are programs now in Western Australia, South Australia, Victoria, and there are, I think, plans to try to get some stuff in New South Wales for native oysters as well, if I remember correctly. But the work that TNC has done in Victoria, they've also been using recycled shell material as some of the base of some of their oyster reef restoration work in the bay as well. So it's kind of a good news story on two fronts of taking advantage of a resource in a way to try to return an environmental benefit for something that had an environmental cost historically.
Great. And just Robert was asking, you mentioned that some of the community feared that the mangroves would harbour mosquitoes. Does that happen?
No. So, yeah, no, not down here. So.
It's pretty clear then.
Yeah.
Right, so
mosquitoes need fresh water, and not down here.
Mm-hmm. Great. Okay, well, that's all the questions that we have had come in. So we might just wrap up then. Thanks again to Stephen for presenting today. And just a little plug that the Earth Systems and Climate Change Next Science webinar will be held next month on July the 17th. And it will be presented by Michael Gross from the CSIRO on climate projections for Australia, learning from past experiences to meet challenges in the next generation of climate projections. So there'll be some information about that coming out over the next couple of weeks, so stay tuned. Thanks to Stephen once again, and thanks for all for attending. So thanks a lot. Goodbye. Thanks.